I'm going to generally be seeking evolution equations for the aggregation of particles. Okay, so this can be an aggregation of some smooth distribution of particles, or sometimes will actually be singular quantities we could think about as particles. So the objective is to show the competition between the length scales, and this problem actually goes back to Debye and Huckel in 1923 when they wrote down the Cahn-Hilliard equation, which is also known as the Debye-Huckel equation. So we'll start with there, Cahn-Hilliard. And Huckel's already given us an introduction to Cahn-Hilliard, so I will give a little bit more information about it. The real objective of this series of talks is the last two. We're going to use the variational method, which is essentially in Felix Otto's paper in 2001, in the special case, which is based on an analog of Darcy's law. You probably remember that Darcy's law says that the velocity of the flow is proportional to the force that you put on it, and the proportionality constant is called mobility. And the force, for example, could be the gradient of the pressure. This analog of Darcy's law, we're going to introduce an analog that applies not just for densities, not just for scalar quantities or functions, but applies for any tensor or any geometrical form you can imagine, which would have even some interesting transformation properties. And we'll get a Darcy's law for the general case. That's the point about the geometry. We're going to use some geometry with these gradient flows and get a more general class of gradient flows than has been discussed before. And we're interested in the formation and interaction of singular solutions. Usually what happens in PDE theory is that the analysis stops when you find blow-up. Blow-up in finite time, okay, sign the paper, ship it out. But for these equations, they're cooked up a certain way so that they will have multiple locations where blow-ups occur, and then the singularities will interact with each other. Okay, and so the rule for the collision of the singularities is something we're after. So we're interested in the formation and the interaction of singular solutions. Okay, so there are two keys to this problem that I just put over here, because they're going to, later on I'm going to say, see, I told you. So the two keys are for generalizing the geometrical nature of the flow. So there's two key ideas. First one, for generalizing the geometrical nature of the flow, we're going to use a concept called Lie derivative. And I'm going to tell you all about it, at least everything you need to know for this problem. And the other thing is, for obtaining singular solutions, going to use non-local mobility. Or let me say, how about this? We're going to use not points, not point-wise quantities. Okay, defined at a point. Rather, we're going to introduce things like mobility, which is defined over so instead we use we'll define flow parameters over blobs. So this will mean that there's some screening function or filtering function that is the average or is the size of the particle that matters, and they will interact with each other, carrying this information that they have some range of interaction. There are ranges of interaction for pointwise also. But what I mean is, if we have a density, okay, and we have mobility that depends on the density, that's going to be transformed into, we're going to assume that the particles are not points. They know about their neighbors. So once they start getting close, they act like blobs, and they stick or they jam. So the size of this screening or filtering comes in, and it's going to go to a mobility which depends on a locally integrated density over a region. So it's going to be rho bar will be some convolution kernel integrated against rho. Okay. And for example, we're going to take K to go like this. Value x. Okay, so this is an exponentially falling range of interactions with width alpha. Okay, so this is going to be a setup. The two key ideas in geometrizing are first bring in some geometry, and the point about getting the singular solutions is to bring in some non-locality. Okay, this is what I mean by non-locality. The point-wise quantities. We'll get equations for point-wise quantities, but we'll actually diagnose them and diagnose the interactions by looking at their averages. Not average over the domain, just convolutions. Okay. Okay. So here's what these lectures are going to cover. So we'll start with Cahn-Hilliard for phase separation. Thank you, Uba. Set everything up. And coarsening of patterns, and we'll discuss then its coupling to Navier-Stokes. Okay, the coupling of Cahn-Hilliard to Navier-Stokes is a non-trivial step. And of course the coarsening is going to influence the flow, and the flow is going to influence the coarsening. Coarsening is when small scales try to become large scales. And it follows like this. Whenever you have a set of low modes in a periodic domain which are unstable, and a bunch more, which are the rest of them, which are stable, and the frequency of the dispersion relation falls, I can do like super route, or it can do like this, like parabola. So this is the way the dispersion relation looks for Cahn-Hilliard, and this is the way the dispersion relation looks for an amplitude equation based on Cahn-Hilliard, called complex Ginsburg-Landau. Okay, so these guys are unstable nodes, and the rest of them are stable. Okay, so that's what coarsening does, is when these higher modes try to come back down to the edge of the threshold of instability because of the nonlinearity. Okay. So I was thinking about this question to Uba. If we have coarsening, then this should happen, and only the first few of these modes should matter. But if we have also events which pump these unstable modes way out into the stable modes, it's going to take a while for the stable modes to find each other, to come back to the unstable modes and arrive at this threshold of instability. And maybe they will find something in the meantime, which is with these other bumps, bubbles, that we were talking about. Okay. So after Cahn-Hilliard, we'll pass to Keller-Siegel. We'll talk about its two versions. One's the coupling between two parabolic equations, and another is a coupling between a parabolic and an elliptic equation. And it's in that elliptic equation that we first see this type of non-locality appearing. Okay, we'll talk about that. And it'll turn out that non-locality is the source of what's called chemotactic collapse, which is the development of blow-up in finite time. And the collapse is, in this case, the collapse is all the way to delta functions, okay, for the density. Okay, then we'll introduce magnetic degrees of freedom and talk about how this type of gradient flow generalizes for them. And we'll discuss the part of the Keller-Siegel model that leads to the collapse, and that will be our preparation for the singular solutions in a geometrical order parameter theory, GOP, for porous media and other more general media. At the very end, I might say a little something about combining Hamiltonian and dissipative structures using double brackets. So everyone knows Hamiltonian's dynamics has a bracket in it. And you can make that into a dissipative operator by taking two brackets. Okay, I'll just talk about that a little bit at the end. My collaborators in this work, which has occurred over the last 6 years, are Vakhtang Putraza and Chesari Franchi, both of whom were here earlier in this program. Okay, so here's the beginning, what Cahn-Hilliard does. So we should write down what is Cahn-Hilliard, even though Uwe already wrote it.
You dropped your microphone. The microphone's on the floor. I mean, it's kind of interesting to hear your feet. Probably we want to hear your voice.
So, for Cahn-Hilliard, I guess we'll call it CH for short. We introduce scalar phase variable. All the variables for now. So it's phi of x and t, which is equal to +1 if a position variable x, this x, is in phase 1, and -1 if the position variable is in phase 2. Here's the equation. You will not be surprised to see this equation. It's exactly what Uwe wrote. d by dt phi is the divergence of some mobility dependent on phi times the gradient of a variational derivative of phi. For example, of a free energy function. So, example, f of phi is integral of 1/4 phi squared minus 1 squared plus gamma squared root 2 grad phi squared. Integrated over p and x over how many, whatever dimensions we need. Okay, so then this becomes equal to the divergence gamma phi and the gradient of this variational derivative. Okay, so this guy f of phi, as a function of phi, I don't know how to, let me do it this way. So this guy here is the double well potential. Looks like this. Where this is phi, and this is x. No, this is f of phi. F of phi is just f out of it versus phi, and it has three equilibria: one at -1, one at +1, and an unstable one at 0. Okay, and this is the thing that drives the coarsening, and this gamma is this thing that this gamma is that length scale between them. If you think about these, so in one dimension, Cahn-Hilliard forms stripes, +1, -1, +1, and they merge. And they merge again. That's coarsening. Okay, and they have a boundary, so they look, the phase between one and the other one looks like this. 1, minus 1, 5, now it's x, and this width, gamma. Okay, so these are much more convenient to work with than sharp interfaces. These are called diffuse interfaces, or phase variables. And they are very stable compared to free interfaces which jump across a step function. So they're approximated a step function by smoothing it out over a distance gamma. Okay, so in this case, that becomes grad y cubed minus phi minus gamma squared Laplacian phi. Okay, and the dynamics in that case, in one dimension they have stripes, and the stripes merge, get wider. In two dimensions, they have patterns, which are sort of stripe-like patterns, which merge and which merge, and they eventually turn into one black blob. In 3 dimensions, you can see it happening here. So we start out with fine scale pattern, and this is time 1, time 2, time 3, time 4, and you can see the forcing occur. So it's really attractive and intriguing. Think about these equations from some kind of biological viewpoint. Okay, we'll talk about this biological viewpoint more. The sort of question is this how zebras and tigers and other animals get their stripes? It's an imaginary thing, but it's interesting. Okay. So let's talk about the connections of Kahn-Hilliard equation to Riemannian geometry. This is another well-known thing. You write Kahn-Hilliard as d by dt of phi is equal to the divergence m of phi grad df phi. And you introduce L2 pairing. So this means that f with h in L for L2 pairing is the integral of f of x, h of x, dx over whatever region. And we calculate some energy. We calculate the dynamics of any functional E of phi. So that is d by dt phi times delta E delta phi. Okay. Okay, and this guy here, take on this formula, this guy is integral of give m phi grad df phi times dE phi. Which we then write as minus pairing of m of phi, integrate by parts. We put the gradient on the dE phi, and we pair it with m of phi is the gradient of the f phi. And we call that metric. So it's gamma of d phi, df d phi, d phi. Okay, so this guy's defining a metric. We have too many things here.
E and F is the same?
We have one too many things.
Not necessarily.
Okay, and so this guy here, I'm going to call a Riemannian metric when m of phi is a positive function. And of course, then the F P, free energy, is gamma of delta F, delta phi, delta F, delta phi, which is less than or equal to 0 by the line above for m of phi positive. Okay, and finally, we can rewrite the Klein-Hilliard equation as d by dt of phi paired with the function in the space dual to phi, which in L2 is the functions. There's gamma df d phi times psi.
Can I ask a question that maybe will clarify? But gamma here is a functional of the two variational derivatives.
Right. It's a functional, and we wanted to define a metric on the space of functions. Because F and E are functionals,
Right.
and they're variational derivatives of functions, and we're using L2 pairing. It's natural, just like summing over indices. Okay, so this is the beginning. And so what I want to do now is let Klein-Hilliard interact with a fluid. Okay, so as the motions of the phases change and the coarsening occurs, it acts on the fluid acts on it. And so what would that look like? For a Navier-Stokes equation, we have 0 d by dt of u, which is the fluid velocity, plus u dot grad u equals minus grad t plus u0, some constant, times velocity of u. And here's the coupling term. Delta f, delta phi, phi, right, and the divergence of u equals 0. So we need the equation for phi, and it's the Cahn-Hilliard equation for the scalar function when it's carried around by the fluid. Okay. So it's divergence. Gradient. Yeah. Phi. Okay, so this is the Cahn-Hilliard acting on the fluid, and this is the fluid pulling the phases around. Okay. So this system dissipates an energy E, which is rho 0 over 2 times the square of the L2 norm of u plus phi. And if you compute the EDT, you get this is equal to minus the integral of mu 0 grad u mod squared plus m phi grad df d rho mod squared dx, which is less than or equal to 0. So the total energy here is the kinetic energy of, here is the kinetic energy of the fluid plus the free energy of the Cahn-Hilliard phase. So let me show you what it looks like. So the research problem now is solve this full system. Okay, numerically, resolve it. But a problem which has already been done is to program u so that it, in what's called a Kolmogorov flow, where it mixes this way for a period, and this can mix that way for a period, and then this way. And here's what you get. So you start out with your coarsening picture when there's no forcing. You turn on the forcing at a low level, and it starts moving these things around, and what do you see? What's the first thing you see here? Right? This is demixing, but the stirring is mixing things up again. Okay, so there's some force level at which the tendency to larger structures turns into a tendency for smaller structures. And as you up that force level, then you get very small structures indeed. Okay, so this is the idea. And I think it's possible now to take a code for Navier-Stokes equations in 2D, code for Cahn-Hilliard equations, and time step them back and forth. And then what you'll see is how the phase coarsening affects the flow, and how the flow, phase coarsening is demixing, and the flow is mixing. So the idea is to study this balance. Cameron, do you have some remark? You just gave me that look. Yeah. Okay. So the first question here. So I promise I'm going to give you some research questions and some exercises. And the first one is for research. It's sort of what we see. Oh, let me write the list. Okay, I have a list of properties. Properties of these solutions when U is programmed to be mixing, two dimensions are the following. So this is the summary of stirred Cahn-Hilliard behavior. So, first of all, steady state is always achieved. To balance of the stirring force, the balancing between advection, stirring force, and coarsening, Cahn-Hilliard. And these features I was showing are nearly at this equilibrium. There always exists such an equilibrium, which you find by setting the partial of this type of t is equal to 0 and solving the system. That's another good point. So for small forcing, everything still looks like Cahn-Hilliard. Because Cahn-Hilliard is dominating. What happens is interesting. Well, for larger forcing, let me say. So for larger forcing, the mixed state is preferred. Okay, so you can see the Cahn-Hilliard coarsened state, and you can see the mixed state. Here's probably the most interesting feature about this. The domain growth always saturates. Right, this is called coarsening arrest. And stirring vigorously enough will break up the domains and produce mixing. Now comes the research problem. Okay, so first part of it is how big is enough? Question mark? Prove it. That's the research problem. And research problem 2 is compute and analyze full coupling. And in order to do that, since this is a PDE, what are the things you need? Boundary conditions. Okay, so in the periodic domain, no boundary conditions around. But in the confined domain, this could be very interesting.
So I think we'll give it 5 minutes. Is that okay?
Is it over?
Well, you started at 11:30.
Yeah, okay. Good. Let me talk about chemotaxis. Just introduce chemotaxis, and we'll talk about it more after lunch.
Can I just ask a quick question, Dan? So in this mixing, you're specifying U with some
Yeah.
sort of stirring motion. Okay.
Yeah.
And then when you talk about solving the whole system,
Yeah.
you're going to inject energy from boundary conditions or with body forces?
Well, this system here is going to keep dissipating its energy,
Right.
right? So you have to produce in putting here some forcing.
Okay.
Yeah. So you force the Navier-Stokes equations coupled to this guy,
Right.
and that drags this guy along, and this.
But you could do that with a mill, right? You could do that
Yeah,
with
that's
boundary
basically
conditions.
the mixing is with the mill.
Right.
It's a Kolmogorov well mill, which has a cosine in this direction, stop, cosine in that direction, alternate. It's a washing machine.
Mhm.
Okay. So chemotaxis is motion I just want to call it cell movement. So the movement of cells. They're interacting with a chemical, I forgot what reactant. Okay, so we have, this is a model of cell movement. Okay, and yeah, cell movement due to interaction of some concentration, n of t of x, which is the number density of cells in time t in position x, and c of t, which is the concentration of this thing, the chemo attractants. So the idea is that cells move to say go up the gradient of this chemical, and as they go up, they also excrete this chemical. So it looks like this. So this is called the Keller-Siegel equation, or the Patlak-Keller-Siegel, because, as always in this business, somebody introduced it a long time before. Somebody else noticed that this was an interesting model too. Some of us in the room probably knew Lee Siegel, who was a constant modeler. He could model anything. Okay, so here's the model called PKS. D by dt of n of x and t is equal to the divergence of d grad n. If d is a constant, this part here is just diffusion. So it's a tendency of the concentration, and the number density to spread out, minus mu in grad c. This is first introduced, this thing was called cross diffusion, because the diffusivity of one species depended on the gradient and the Laplacian of another. And d by dt of c, of x and t, has an epsilon in front of it. And when epsilon goes to 0, it's an interesting limit. And that's equal to alpha squared Laplacian c. Alpha squared is the length. Alpha squared Laplacian is dimension free. And minus gamma c plus beta n. Okay, so this guy mu is sensitivity. I'll stop now. Just ask you to count the number of parameters in this problem. Questions?
This looks like a reaction diffusion equation. Does it have an energy law?
This one here, does it have an energy law?
Yeah.
Yeah. Yeah, I think so. Let me see if I wrote it down. Yeah, I'll answer that question later. Any other questions?
We're finishing, right? Okay, questions?
Yeah, I mean, there you wrote that by steering you arrest coarsening. I was wondering what is the distribution of the main sizes, and then when you say about strong steering and so on, if that steering has to be in order to arrest the coarsening of the size of the system size, or whether a local kind of.
So the Cotton-Hilliard is trying to make phase domains larger. And the stirring is trying to break them up. Okay, and at a certain point, the stirring balances the Cotton-Hilliard to coarsening, and then the coarsening stops. And if you stir more, then with certain parameters, the Cotton-Hilliard cannot keep up.
But what is the length scale of your steering, or what are you calling steering? Is a global thing at the level of the whole system? If your system is the universe, how strong you have to steer?
Probably the system's not the universe. Some periodic domain.
What?
Some periodic domain.
Okay.
Okay. Or, yeah, let's start with that. Because I think that's what the results of the numerics showed, was that there is a balance between mixing and demixing at which the coarsening stops. And it was a question about coarsening arrest in the literature, and this answered that question.
Seems to me, Darrell, that a significant fact is
that when you couple the velocity field to the phase field, you've raised the order of the problem from a second order in space to a fourth order problem in space. And in that situation, you typically get oscillatory tails of your, bubbles, and then those oscillatory tails can lock and freeze the bubbles in place, and thereby preventing coarsening from proceeding forever. And so that's another mechanism for arresting coarsening, just by raising the order of the problem.
Oh, I see. I know linear analysis of this system, but I think, the only linear analysis I know is when the system is, when this U is slave, is governed, is prescribed. I don't know of any numerics or analysis of the full system. It might just be because something's happened in the meantime, but I don't know about it. You might Google that if you're interested in this problem.
I'm all ready for the fourth order equation, for the phase field equation. Aren't bubbles stable? Doesn't it tries to minimize curvature in 2 dimensions?
Are you talking
It's
about
already
this term?
fourth order term.
Yeah, that's a fourth order term. Is that the term you're talking about?
Yeah, I mean, you have a second order term in that equation and another second order term in the U equation.
Oh, but this one even is more,
Together.
because this has Laplacian phi in it. So it's already fourth order. Right? You have to grab Laplacian. Yeah, because dft phi has some phi terms and a Laplacian phi term.
Other questions? Okay, let's thank Darryl again.